Lecture 8, Timers and Counters. Okay, so far we have seen how AVR is working and how we can use assembly language or C language and some hardware connections related with external memories and so on. Now, from this chapter on, we will concentrate on the resources inside of an AVR microcontroller that we can use for various applications. And one of those are timers and the counters. So many applications that we are using in embedded systems, they need to count an event, or maybe they need to generate a time delays. So we have seen that we can create loops and we can generate these time delays. But inside of the microcontrollers, there are counter registers, which is serving this purpose actually. And this is what we are going to see, how these counter registers can be configured in order to have a time delays or count an event. So we'll introduce the generic counters and the timers. Then we'll talk about how AVR timing is used and the accurate calculations of the time based on the instructions and the executions of these instructions. Waveform generation, we'll just slightly talk about it because we are going to see it in another chapter later on. If you want to generate large time delays, what can we do? Because our registers are 8-bit registers. If you want to have larger delays, what do we need to consider? CTC mode, which is also related with the timers, compare, match. And we'll also talk about various specs of the timers because we have got different timers in AVR microcontrollers. And we'll also talk about how counting an event can be done. So if we talk about counting an event or maybe a generating time delay, let's say with the counting with an event. Now we connect an external event source to the clock, like this one, okay? And we can start counting the content. So the content of the, whenever it's something happened over here as a external source, the clock is going to tick. So in a way that the counter register, if you do remember from logic design, it will start to increment. Okay, so the counter is incremented, and in this way, the content of the counter represents how many times an event has occurred actually. Now, that's one thing that we can do with the counters. And another thing is when we want to generate time delays, we connect oscillator to the clock pin of the counter. Okay, so here is a sensor or maybe something else that we can use for counting an event, or alternatively, we can connect an oscillator, which is actually a clock generator or clock, so that when the oscillator ticks, the content of the counter is also incremented. And as a result of this, the counter register represents how many ticks it has been occurred from time we have cleared the counter. And as we know the speed of the oscillator in the microcontroller, we can easily calculate the tick period from the content of the counter register, and we will know how much time it will be elapsed. So one way to generate a time delay is to clear the counter at the start and wait until the counter reaches to a certain number. So, for example, when we want to, let's say, generate a delay, okay, and we have a frequency of 1 megahertz clock. Now, the content of the counter registers increments once per second, microseconds. So if we want a time delay of 100 microseconds, that means the counter has to wait until it reaches from 0 to 100. Because if each tick is 1 microsecond, okay, if it's incremented in 1 microseconds, that means we have to set this limit to become 100 so that we can have 100 microsecond time delay. Okay, so as I already mentioned, we need timers for delay generating, we need timers for counting, we need timers for waveform generating, and we need timers for capturing for like external timing events. And AVR microcontroller that we are using at Mega 128 has got four flexible timers. Some of the AVRs has got more than that, but 128 has got four flexible timers. Timer 0, timer 2 are 8-bit timers, and timer 1, timer 3, they are 16-bit timers, which we are going to introduce all of those and see and show how we can use them. Now, what we have seen in the previous chapter, we can create these delays, timing events, but this is actually done by the hardware. So we have a specific hardware, which is a counter over here, that we can use for timing events, independent of other code executed in the microcontrollers. And many embedded applications, as I already mentioned, would like to time or count events in the background in addition to doing some other tasks. So each of these timers in the Atmega microcontroller, we have got some registers that we need to configure, like TCCR. TCCR is the one of them, which is used for control register. It's used for setting the modes of the operation. And we have got TCNT, which is the timer counter register. It's actually the where we have got the value over here. So timer overflow flag. Now, in the microcontroller, there's a flag for each of the counters. So the flag is set when the counter, for example, it overflows. And we have to clear it by the software. And a second method is we can generate a time delay. So we can load the counter register and wait until it overflows and flag is set. Okay, so there are alternatives over there. We can use timer overflow flags. TCCR, as I already mentioned, is the control register. OCRN, output compare register. We can set a value over here and we can compare if the TCNT value, the counter value, is reached that point. If they're equal, then we set output compare match flag. Okay, and these ends, they can be either 0 or 2 for 8-bit counters, and they can be 1 or 3 for 16-bit counters. And all timer registers are byte addressable I/O registers, which you can find them in the I/O table as well. So before I move on, I want to give you some simple example related to this. So for example, in a microcontroller with a frequency of 1 megahertz again, if we have an 8-bit counter register, and if we want to a time delay of 3 microseconds, so in order to have 3 microseconds, now the maximum that this 8-bit register can get is 00 to FF, right, as a value. So I just need, as I know from 1 megahertz, we need to have 1 microseconds for each tick, as we already said in this example. Now I need 3 ticks for 3 microseconds. Now, what will be that timer value or timer counter value that I need to set in order to count it? So from this point on, it's going to reset and restart. Okay, so I need to set this 3 clocks before it sets to FF. Okay, and in the third tick, it has to overflow and content of the register has to become 0 again. So that means if I set my 8-bit counter to FD as a value, after the first tick, this becomes FE, okay? And after the second tick, it becomes FF. Okay, so tick 1, tick 2. Now we need another one. So on the third tick, overflows and restarts. So I can create a 3 microsecond, 3 microseconds from the timer register, 8-bit timer register, by setting the timer register value to FD. So one clock tick, FE, one clock tick, second clock tick, FF, and the third one, which is 3 microsecond, it becomes 0 and starts again. Okay, so this is how we generally use timers, and we are going to see them in details as well. Okay, so as you can see, this is the architecture of the internal architecture of AVR, which is responsible from timer counters, and TCCR, TCNT, and OCRN registers that we are interested in. TCCRN is here, which is the control register. TCNT is over here, and OCRN is here. Of course, we have got some other like output compare match pins over here, the oscillators and the prescalers, which we will talk about it later on, about these as well. Now, if we are using 8-bit timer, we can use timer counter 0 or timer counter 2. Okay, they have a similar architecture. Let's talk about timer counter 0 first. So internal synchronous clock, which is a clock IO or microcontroller clock, or we can use external asynchronous low frequency 32 kHz oscillator source from TOSC 1 or 2. So if I call back from here, from these ones, we can use an external oscillators. But we have to be careful over there that we need to set some pins in the ASSR register, which is the asynchronous status register. Now, the output of clock select logic, which is clock TN, where n is 0 for the timer counter 0. So this is coming from here. And CPU can read and write to the TCN3 regardless of the clock T0 is running or not. Okay, so we can write the values over here without this clock as well. So some of the signals that we are interested in. So the count over here is used to increment and decrement enable. So based on the value over here, you might need to increment or decrement. So that is controlling that. Direction up or down has to be given. Clear, we can reset TCNT 0 register. So it means it contains zeros and it counts up from each pulp, and the contents of the timer counter register can be accessed using this TCNT register. You can either load a value into TCNT register or you can read a value from it. And we also have top and bottom. So in the control logic, top and bottom inputs over there. So it's just giving a feedback if it reaches to the maximum level or to a minimum level. So as I already mentioned, each of these timers has got their own timer control registers for setting the modes of the operation. So you can actually specify if you want, for example, the timer 0 to work as a timer or as a counter by loading proper values to the TCCR. We need to configure it, which I will do that later on as well. And as we already mentioned, each of these timers has got output compare register, which is OCRN, which is over here. The content of the OCRN is compared with the content of the TCNT. And when they are equal, OCFN flag is set, which is the output compare flag. And we can use it that way in CTC mode. So here is the TCCR register and how we can use it to configure it. Now, the first bit of the TCCR register is FOC0, which is known as force compare match. If you want to generate a wave, you can use that pin, but normally in a normal operation of the timer, we just set it to 0. Then we have got VGM00 and VGM01, which are timer mode select, which I'm going to show you in a minute what those modes are. And we also have COM01 and COM00, which is compare output mode, controls the waveform generator again. And we have got a clock selector. So clock selector, which is the last 3 bits of the TCCR, it is used to choose the clock source actually. So you can see how they can be configured if you are using a prescaler or not. So no prescaling, you just need to set this to 001. If you are using a prescalers, you have to do those calculations in order to set them to different prescaling. So why do we need prescaling? If you want to slow down a clock, you might need a prescaler. So for example, if we look at the figure over here, where there is no prescaler, the clock is running, and while the clock is ticking, the TCNT value is actually incremented. So when it reaches to the maximum point, the timer overflow flag is set. And then it goes overflow, and timer overflow flag is still set. And then we start again while the clock is ticking. If you are running a prescaler, let's say your clock is too fast and you want to slow down your counter, and you have to slow it down, or let's say clock dividing over here. So for example, on the rising edge of the clocks, that you can prescale it down by 8, for example. So after the 8 clock pulses, you have 1 clock generated. 8 clock pulses, 1 clock pulse is generated. So we are slowing down it. And then the timer works based on this prescaled value, and you count up through that. So oscillator uses as a clock source, and timer counter acts as a timer. Now, the timer counter too, as you can see, if I can compare it with the previous one over here. So this is architecture for the counter 0 or 2. And there's one thing which is significantly different, is this part of the over here. So this is a external clock. Okay, so we can have a TN pin which is connected, and we can detect the edge. Now the timer counter has this configuration, which is the pin T1 and T2, which we can use it for external events as well. So the control register for timer counter 2, as you can see, 110. So this one has got 8, 32, 64, 128, 256, 124. And timer counter 2, 8, 64, there's no 32, 256, 124. And we have got external clock that is coming from the polling edge or the rising edge, that we can configure it in order to use it, which we are going to see them later on. But this is only valid for 8-bit counters. This is only valid for timer counter 2. Okay, and that's the part of it. So the rest is just the clock divider. If you don't need a prescaling, you just set it to 001, and same as timer counter 0. Another important thing in the timer counter is the output compare. So if we are using OCRN registers, we set the value of the OCRN register. For example, I want to set it to 50. And TCNT value, when it reaches to 50, it checks it for each of the values. 0, compare with the OCRN. No, it's not matching. 1, 2, up to 50. When it reaches to 50, OCFN flag will be set in the next clock cycle. And you can use also interrupts so that whenever the OCFN flag is set, then you can do some other stuff. And so we can use it this way by output compare. Or maybe we can generate different waveforms based on the waveform generation modes, which we are going to see that later on, and output compare modes. And we can also use FOCN pin, which I already mentioned with the TCCR control register, that we can force the output compare value to be overwritten. So CPU write to the TCNT blocks, compare matching for one clock cycle. So everything is happening over here for the waveform generation. We set everything related to the waveform that we are required. I'll talk about these in details later, and when it is that the comparator is checking, when they're matching, it sets the flag output. Okay, and there's the waveform generation part of it. So timer counter control register, you can see the VGM is 0 or 2 8-bit registers, counters. We have two timer mode pins in the TCCR, which is VGM20 and VGM21. We have the similar stuff in the timer control 0, VGM00, and VGM01. They are serving the similar stuff. So when they're 00, it's the normal mode. When they're in 01, it's the compare, clear timer on compare, PWM modes, and the fast PWM modes, which we are going to talk or discuss them later. Okay, so all modes except the CTC mode in this configuration. So what will happen is in the CTC mode, we count up and we check the OCRN value. So whenever we matches the OCRN value, OCFN flag will be set. Okay, and without a prescaler and with a prescaler, this is how we can implement it. We'll do examples, we'll explain how these are working all together in an harmony so that we can use it for counting the time and also the events. Now, when we talk about timers, we have said that we have got two modes actually. So those two modes are CTC mode and the normal mode, which we call it. Now, what is the difference is, in this mode, the content of the timer counter increments with the clock, and it counts up until it reaches to the FF, because 8-bit register can have maximum of FF. And when it rolls over, as I already given in the example, to 00, it sets high the TOV flag, which is timer overflow. Okay, so we can see this like, if I can draw it properly, this is our TCNT 0 register. So the maximum is hex FF for 8-bit counter. Now, what will happen over here? Let's say we start from 00, 01, it goes to FE, FF, let's say, okay? So we are jumping from one to the other. So we have some in between, and we reach to FF. Now, what will happen is, starting from 0, it counts up to FF. When it reaches to FF, it goes back, it overflows. So at this point, where it overflows, it sets the timer overflow flag. Okay, so when it rolls over from hex FF to hex 00, TOV flag is set to 1. Okay, now the timer counter increments with each clock. It counts up until it reaches the maximum of 0 FF, and when it reaches to FF, it rolls over and TOV flag is set, and it counts up again and down again, up again and down again. So at these points, TOV flag is set. Okay, so this is how normal mode of operation is. This is known as normal. Now, other mode that we have to use is we have to set, which is known as CTC, clear timer or compare match. Now, similar waveform, but one thing that we need to be careful, 0 hex FF again is the maximum. Okay, this is somewhere here. This is again TCNT 0. Now, for example, we can set the OCR 0 value somewhere here to be something else. Okay, that is FF. I can set it to DF or DE or whatever you want to call it. Now, again, I start to count 0, 0, 0, 1, 1, 0, 2, and it goes up to the value that I set with the OCRN. Okay, so 1, 2, and it goes like that. So what will happen now, rather than going up to FF, when my TCN2 value matches with the OCR 0 value, it goes down and the OCF 0 flag is set. Then it goes up again and down again, up again, down again, up again, and down again. So at these points, OCF 0 flag will be set. TOV flag, it's always going to be 0 with CTC mode. Once again, we can actually set those modes. We can configure it so that either we run it in the normal mode, which is 0, 0 with the VGMs, or in the CTC mode, which we can set it to 0, 1. So this can be demonstrated on the slides as well. As you can see, once again, if we are in normal mode, we just count from 0 to FF all the way up. When it is overflows, it sets TOV and flag. So you can set this where to start from. You can start from, for example, 10 to FF. Depending on what you are going to count, you have to calculate that, and you have to set that TCNT value, so it will count from that point to the FF, and then when the overflow occurs, the TOV flag will be set. Or in the CTC mode, OCRN value is set, and it just keep constantly checking for if these two are matching. The TCNT is incrementing and checking against the OCRN. When it matches with the OCRN, it sets the OCF 0 or OCFN signal flag to 1, saying that there's a compare match. Now these in non-PWM modes, we can use the compare match outputs in order to generate some waveforms as well. So we can toggle it 1 to 0, 0 to 1 on the compare match. We can clear it, set it to 0, we can set it to 1. So these are all applicable in the timer control registers, which we can modify the control or the operation of these timers. So another important thing which we are going to see in the next chapter, which is about the interrupt flags. Now, each of these timers, the 8-bit timers, we have got some flags, like timer 0 has got timer overflow, which is in the normal mode flag, and timer output compare match OCF 0 flags, or for timer 2, TOV overflow and compare match. Now, depending on the mode that we are using, we can actually monitor these flags in order to check when the operation is having the completed the count, so that we have the value and so on. So if we are using OCF, we can set when a compare match occurs between the timer counter 02 and the data in OCR 02. Cleared by hardware when executing the corresponding interrupt handler. So we have to write some software over there. When the timer overflow interrupt occurs, do perform these operations. Or it can be alternatively cleared by the software by writing one to the flag of it. And the timer overflow, it sets when overflow occurs in the timer counter, and cleared by the hardware when executing in the corresponding interrupt handler. Alternatively, again, it can be cleared by the software. So if we summarize the 8-bit counters, timer 0 and timer 2, we have got control register TCCR0 and TCCR2 in the AVR, and we have got two TCNT timer counter data registers, which we put the values in there, TCNT0 and TCNT2. We have got two overflow flags, TOV0 and TOV2, and two output compare flags, OCF0 and OCF2. The modes, only difference is the timer counter 2 also has external clocks that we can feed into the timer. But timer counter 0 is just using internal clocks with prescaler modes.